Okay, let's look at another example of an improper integral having infinite bounds. Um, and so remember, if we have the bounds at infinity, we're going to rewrite this as the limit as b approaches infinity of the integral from 0 to b of x e to the negative x with respect to x. And you can just remember that wherever your problem area is, you can always write it the same. So even if your problem was a negative infinity here, as long as it's just one or the other, you could just write this as the limit as b approaches negative infinity and put the b down here. In other words, you don't have to keep switching back and forth between variables, especially if it's confusing. But once you get it set up this way, this is kind of like a three-part problem. There is an integral, which we're going to do first. We're going to work from the back forward. So we're going to integrate, then we're going to put in the bounds, and then we're going to do the limit last. So let's get started doing the integration. When I look at this, it's not a basic rule, and it's not going to be a U substitution. It's not a trigonometric form, but it does look like two separate and distinct functions which cannot be combined. So that leads me to the integration by parts. Now, in your last or in one of your earlier videos, I showed you a shortcut way to do these as long as one of your parts will actually differentiate down to 0, and it's a table form. Your table form are going to have three different columns to it. You have your alternating signs column, you have the U column, and you have the DV column. Now we start by picking our U. Our U is the thing that's going to differentiate down to 0. Always write the U in there. Don't do the derivative and put it in there. Start with the actual U. And then you're going to differentiate that down to 0. So the derivative of x is 1 and the derivative of 1 is 0. And that tells me how many rows I'm going to have in my column. Then let's go back to our original integral, and we notice that we picked this to be our u, so that remember that the rest of this then will become the dv. And in this case, we're just going to shortcut it and write it as an e to the negative x. Now remember, it's the u column that you differentiate, and it's the dv column that you integrate. So we're going to integrate e to the negative x. That's easy enough. The integral of e to the negative x is negative e to the negative x. It switches signs back and forth. So when we integrate it again, it becomes a positive e to the negative x. And then your alternating signs simply mean you start with a positive, then go negative, positive, and you would continue just depending on the number of rows you have. Then to come up with our answer to our integral, we simply read this chart across and down, across and down until you run out of down spaces to go to. So let's go back and put this information in. So this is going to be the limit as b approaches infinity. Remember, we haven't done that yet. The only thing we're doing now is we're going to do the integration itself. We're not even going to put the bounds in at this point. And remember that when you're doing this, you're just going to read those things directly off of your column or your table by going across and down. So what we're going to have here, it looks like x times a negative e to the minus x. So that's minus x e to the minus x. Then using the next one, that's going to be a minus 1 times e to the minus x, or just minus e to the minus x. And notice we haven't put in the bounds, so we're going to need to put in those bounds between 0 and b. Now, as you saw in one of the earlier videos, we get into a problem when we start putting in negative exponents into things. So what you might want to do before you get started is just go ahead and rewrite this and make those exponents positive. So this is going to be then the limit, as b approaches infinity of a negative x divided by e to the x, and then minus 1 over e to the x. And as a matter of fact, since both of those have the e to the x on the bottom, I could actually combine this to give me the limit as b approaches infinity of a negative x minus 1 over e to the x, which I will look at between 0 and b. And again, notice that I have not done anything so far but the integration. Next, I'm going to put in the bounds, and so we're still keeping that limit. Remember, you're not losing the limit until you actually take the limit. And then we're going to start by putting in the b. So we're going to have a negative b minus 1 divided by e to the b, minus, we'll put in the 0, minus 0 minus 1 divided by e to the 0. And of course, this is equivalent to taking two separate limits. So this would be equivalent to the limit as b approaches infinity of negative b minus 1 over e to the b minus the limit as b approaches infinity of, that looks like negative 0 minus 1, so that's minus 1 over e to the 0, which is 1. So let's go ahead now and apply the limits. Well, this second one is easy enough because there's no place to put an infinity. This is just minus a negative 1, which is going to give you a plus 1. But let's look at this first limit. When I plug in infinity, I'm going to get infinity over infinity. And so what do we do when we get infinity over infinity? Well, one thing we can do is use L'Hopital's rule. And then this becomes the limit as b approaches infinity. We're going to take the derivative of the top of this with respect to b, which is going to give me a negative 1. And the derivative of e to the b with respect to b is e to the b. And when I put a huge number in the bottom of a denominator by applying the limit and putting in infinity, this entire quantity will go to 0 because any number divided by infinity is 0. So we get 0 plus 1, which is simply 1. So our limit here does indeed converge, and it converges to a value of 1.